because it's a metal and because that makes it a conductor, if I have a solid metallic sphere, automatically inside here, the electric field is 0. It has to be. Again, because of the rules. That doesn't mean the charge on the conductor is 0. I can tell you that that charge has been added to a conductor. Let's say the conductor has a charge of positive Q. All that means is that on the surface, the very surface of the conductor, there's a net set of positive charges, all at the surface. I told you that also. On a conductor, charges live at the surface. They're not inside the material. In free space, like we have here, those charges would all arrange themselves on the outside. And since I said positive Q, I should make all these little positives, not little negatives. So let's say that they have positive Q. And let's just add a few little details, like let's say that this sphere, solid sphere, has a radius of r. Gauss's law still has to work, as it is a law, and it doesn't matter if there's material there or not material there. So in keeping with Gauss's law, if I choose a Gaussian surface, let's say I choose a Gaussian surface like this, randomly placed somewhere inside the sphere, I place a Gaussian sphere. How much charge would be enclosed in this sphere? Based on the rules that I've given you, there'd be no charge inside the sphere, no net charge inside the sphere. Right? In a conductor, all free charges are moved to the outside edge of the sphere. They're all around the surface of the sphere. So I would never be able to, in a solid metal structure, be able to enclose any charge, which forces the left side of Gauss's law to be 0, reinforcing the idea that the electric field inside here would always have to be 0. And we're saying Gauss's law still works here. We all okay with that? Now, I could consider a different Gaussian surface. This Gaussian surface. This Gaussian surface is clearly at a distance that is greater than r. Okay, let's say, little r. It does enclose charge, doesn't it? So based on Gauss's law, the enclosed charge here would be Q. This is what is enclosed in my sphere, my Gaussian sphere. And based on what we did 2 days ago, I don't think it would be a hard stretch for us to look at the flux and say that this flux conforms to what we did with the point charge. Do you remember? And the electric field from the sphere is probably this way. There'll be no electric field inside the sphere. I'm careful not to draw lines inside the sphere. And I don't know why I ended that electric field at the Gaussian sphere. They would penetrate space like so. And based on what we talked about with area, I think we could all agree that the area and the electric fields would be lined up. Right. Just applying the rules of Gauss's law, bless you. Bless you. So probably write this as electric field uniform, because the charges are all spread out uniformly on the surface of the sphere. Sum up the area and get 4 pi r squared. I'm just repeating what we did for the point charge. Are we all okay so far? So Q enclosed equals epsilon naught times the flux. So I get Q equals epsilon naught E times 4 pi r squared. Electric field equals 1 over 4 pi epsilon naught times Q over r squared. Just using Gauss's law, applying it to this circumstance. But this is only true if R is greater than R. Right? Because if R is less than R, the electric field equals 0. You guys understand what I'm saying? See how I'm trying to deliver this? There's an abrupt change at the surface. If I go from an electric field of 0 to an electric field that is suddenly not 0, because I'm just outside the sphere. But if I'm in the sphere in any way, the electric field is 0. In fact, you could be asked to plot the electric field as a function of R. Marking the radius somewhere, this field will just be a flat line at 0 until you got outside of the sphere, and then you would have something like that. All right, back to this. Not that anybody's going to watch these videos. I don't even know why I'm bothering. I should just go back to using a dry erase marker. Did you follow this argument okay? Now, because I'm trying to be pretty deliberate, but I want to switch it up a bit, okay? So to switch it up, I'm going to go. And draw the sphere again, because I need the sphere. So there's my sphere again. And I'm going to put a point charge right here, Q. For this moment, let's just assume the sphere is neutral, but it's still a solid conducting sphere. And say this distance is x. All right? There is clearly an electric field a distance x away from my point charge, right? Has to be. What's the electric field inside the sphere? 0. Now, hear me out. How can it be 0? Now, I know that I told you it has to be. That's the rule. And because that's the rule and it's a priority, we always say that first. Before you do anything else, the electric field inside any conductor is 0. Well, why is it 0? Well, the only way it can be 0 is if the charge that's outside the conductor somehow influences the charges in the conductor to make the electric field 0. That's what happens. Right? We have a strong positive charge here. That strong positive charge is going to reorganize the charges on the sphere, causing the negative charges on the sphere to move to one side of the sphere and repelling positive charges. So they'll be on the other side of the sphere. If the sphere wasn't here, well, I guess that means I take everything. I didn't mean to take everything. Just figure this stuff out. I don't want to take all that. I just want to move that a little bit. If the sphere wasn't here, there would clearly be an electric field in space from my point charge, right? Something like, I don't want to use blue, I want to use red. I've been making electric fields red today. So there, electric field, electric field, electric field. You're getting the point, right? How many of these little lines do I have to draw? Is that enough lines? Is that enough? So these are all, electric field lines. They fill the space around my point charge. When I bring my sphere back into position, it has to manipulate the charges on its surface. They're still going to be on the surface, but it's going to pull those negative charges closer, and it will push positive charges back or reveal positive charges, because positive charges we know are part of the protons, blah, blah, blah. But you notice what happens, don't you? By doing that, the charges on the surface of the sphere work to create a counter-electric field, to counter the applied electric field from outside. And this happens regardless of the strength of the exterior electric field, which is pretty amazing if you ask me. We good so far? Any problem with that? Add a wrinkle? What if my conductor is a shell, right? It's got an empty space in the middle, and with that empty space, there's, just nothing in here. Still have my point charge out here. What do you think the electric field would be here? It's not inside the conductor any longer, but it's inside the shell. Interesting, huh? Would you believe me if I told you it has to still be zero? It would. It would have to be zero still. Remember, the charges live on the surface of the conductor. And because they live on the surface of the conductor, they still form an electric field counter to the applied electric field. That still has to take place. So because the charges live on that surface, they've created the electric field that counters the applied electric field inside the shell. In fact, this is called a Faraday cage. Somebody used these words a couple days ago, but this is what happens. A Faraday cage means extra electric fields can't penetrate Faraday cages. This is an easy way to block cell phone transmissions, right? Just put them inside an aluminum foil box and nothing gets in. Stuff gets out, but nothing gets in. That's why right now, what do you guys got? 1 bar? Maybe 2? Look at your phones real quick. Who's got more than 2 bars in this room? Love this room. If you got more than 2 bars, you're probably getting close to the door. Or you must have a different service. Generally, most people in my room have 1 to 2 bars in here. Now, this is not a perfect Faraday cage. Got windows, right? But I have a metal door, and there's metal rebar reinforcement in the walls. It's not a solid conductor, but it is definitely a conducting lattice, which acts in many ways just like a solid conductor would. It's not perfect. That's why some of it's leaking in. That's why you guys got 1 or 2 bars. But have you ever seen some of those little devices that you put your phone in that are designed to make it not receive any signal? In fact, people use it to try and steal stuff, actually. You want to steal that book from the bookstore, you find one of them aluminum foil baggy things, because you know that little sensor's somewhere in the book, right? That little square thing that you find every once in a while. You think it's just a weird bookmark. You've seen what I'm talking about? Who's seen what I'm talking about? Well, maybe not everybody reads books, but they're made out of paper, And they put this little square thing in there, and you pull it out and look at it. Just peel the back, you'll see a little grid pattern. It emits an electric field. They just drop it somewhere randomly in the middle of the book, and then you walk through those two little panels, and an alarm goes off, right? Well, what do you think's happening there? Well, I want to block it, so maybe I can find a way to block it, shield it, you know. There's ways. But I want to bring up first the idea of the Faraday cage. Inside any conducting shell, external electric fields are blocked. This is not so much a rule, it's a consequence of the electric field inside a conductor being zero. And I don't have to be all symmetrical about it. This hole can be anywhere inside the conductor. So no matter where the hole is inside the conductor, and no matter what size the hole is inside the conductor, if the hole is empty, the electric field inside the hole is zero. All right? Rules of conductors. Oh, I knew it. Go ahead.
I'm sorry.
No, you're not. Don't say you're sorry for asking a question. That irritates me more than the question.
Okay. Earlier you said that charges could be...
I chose a sphere because of the uniformity of the sphere. It's easy to work with. You start dealing with shapes that are more unusual, that have points on them, you'll still have an electric field of zero inside them, as long as they are a complete chamber, you know, no openings, no breaks. But the distribution of charges has to become more complicated in order to maintain the electric field of zero inside. So you can get accumulations of charges that are closer together due to the shape of the device. A sphere makes them spread out in a more uniform way, but you start to get a more complicated sense of the arrangements of the charges if your shape is different. We're going to look at some examples of that, not today because we will run out of time, but in the future. So I want to continue this, if possible, by having you consider a shell of charge. I'm sorry, a conducting shell of neutral charge. Okay, so it's a conducting shell of neutral charge. So the net charge on this shell is zero. All good? But what I want to do is place inside of it a point charge. Okay? So there is a positive point charge inside my conducting shell. Now, in this circumstance, the electric field in here would not be zero. A simple Gaussian surface test would prove that there would have to be an electric field in this region of space. All I'd have to do is pick a Gaussian surface that would enclose the charge, and I would immediately have an example that I could use to determine what the electric field inside this region of space would have to be. And since we just did that, I don't feel it's too much of a stretch to say the electric field due to that charge had to be 1 over 4 pi epsilon naught times q over r squared for r less than the outer radius of my, my shell. Right? That's just the result of Gauss's law. So there would be an electric field in this region of space inside the shell. Would there be one outside the shell? Interesting question, isn't it? Let's consider the possibilities of what happens under this circumstance. Let's take my let's take my shell and make it that big. Okay. What's the electric field along the blue surface? Has to be zero, right? We are inside a conductor, so the electric field has to be zero. Gauss's law means the flux on that blue surface has to be zero. Let's just put some terms to this. Let's say that this is RA, and all the way to here is RB, and we're somewhere in the middle of that, little r. Is that okay? Just so I have some terms. Along my Gaussian surface, the flux has to be 0 because the electric field is 0. Everybody good so far? Understand what I just said? It's the overriding priority. You must make that true. Now, Q enclosed has to equal epsilon naught times 0. Right? The flux is 0. Well, this must tell you something. What this must mean is that there is a charge on the inside surface of the conductor. There has to be. It's the only way that the Q enclosed can be 0 is if there is a negative Q spread out on the inside surface of my conductor. Has to be. Now, I know you have to go, but you understand that if there's a negative charge pulled to the inside of the conductor, but the conductor was neutral, that must mean that there's a positive charge on the outside surface of the conductor. That generates an electric field this way. So that's why it's an electric field of 0 inside. Is there an electric field here?
Yes.
There has to be, yeah. Because if you put your Gaussian surface out there, does it enclose any charge? It does, so there must be an electric flux. So even though this now cancels out, the Q in the middle and the Q on the inner edge, the Q on the outside of the sphere is producing an electric field outside of the sphere. All right.